You guys have no homework for tonight unless you want to start. Okay. So we've talked about limits. Let's talk about this function. Okay. I'm not going to just go over each section. I'm going to focus on.
Oh gosh.
So they're going to ask you to do some limits in this section with like tables and different things. So you can go ahead and find this with a table. A limit is the primary mechanism of calculus. It wasn't around even when Newton and Leibniz first developed their stuff. It was developed later to make things more streamlined. Newton and Leibniz didn't think about like as you approach points. Newton had this weird, Leibniz had this weird idea of infinitesimal quantities. He thought that things that were infinitesimally small actually existed, and he used those kind of arguments, and they're really complicated, hard to use. This idea of a limit's much better. So this limit's supposed to be approaching what number? Negative 3. Does that mean we want to find out exactly at negative 3 what happens?
No, right before.
Right before or?
Right after.
Right after. We care about the neighborhood, right? When we talk about a limit, and we say like, okay, here's a function, let's say we've got x squared, and we say we want the limit as x approaches 1 on x squared. We're not talking about, we don't care what happens at 1. That was a pre-calc issue. At 1 you get 1. We're talking about in this area, as you get really close that way and really close that way. That's what we want to know about.
Yeah,
we want
so
to know
you
in
get
the...
to, like, point
Yeah, exactly. We want to know what happens to the function in the neighborhood of that point. We don't care about it if it actually happens at that point. Yeah, that might be useful too, but the limit is this other concept, okay? So when they ask you to do a table and they give you values that are like, what kind of values do you think they're going to give me in this table they want us to look at?
Negative 2.9.
They're going to give us like negative 2.9 and then negative 2.999 and then what?
3.01.
Yeah, and then etc. So if you do one or two of those at the table, that's fine. What do you really need to look at? You need to look at things really close to negative 3. So if you want to ignore the tables on those, I'm fine with that. I would personally put this in y1 and say, what is y1 of... Don't mess around with this stuff. Go negative 2.9. Get really close.
Wait, where are you putting this in exactly?
That's table set, isn't it?
Variable.
So yeah, so you're putting on y1 and then you're going to the table. And
Yeah.
You're going to do that with the table. Okay.
Well, I'm going to do this on the home screen. Just go y1 from the variable button. Okay. I'll show you it tomorrow. If you guys need to example, we'll do it tomorrow. Okay. But on this problem, by the time we get there, I bet we're going to get like, that's equal to, from the calculator, negative point.
Oh, I see.
2.4444444. So what do you think this limit actually is?
Negative 2.5.
Which is negative 1/4. So sometimes you have to make a little jump of logic. Sometimes the calculator actually just tell it to you because it gets tired of rounding and it's just like, you know what, this number is really negative 1/4. I'm going to tell you that. Okay, but you've got to be able to make that judgment call.
Or you can hit the fraction button.
You can use the fraction button to help you. Okay.
You just personify the calculator.
I forgot my calculator's name.
Okay. So let's talk about some other issues.
So I guess it's real.
So what are some issues with limits? We had limits that don't exist, right? You guys remember that? There's different ways it can happen. I want to clarify
It'll
all the
say
different
error.
ways. Yeah. Limits can fail to exist in a variety of ways. So let's look at those.
Asymptotes, like jumps.
Yeah. So let me just give you a couple pictures.
Is that number 1?
Yeah.
It's kind of big.
Okay, so these pictures I think describe all the ways that a limit could not exist. So if I take, on this one, if I take the limit as x approaches 2 of g of x, does that exist? We're talking about in the neighborhood of 2, real close to here, do you get a limit? And the answer is no.
And that's because they're not both built in.
Because if you're writing along the function this way, you get to one value, right? Maybe that's 1.
Oh, okay.
You have to lift your pencil.
As you're writing along the function this way, see, think of them both at the same time. You get to a different value. If the values from the left and the right aren't equal, the limit doesn't exist. So something like that, a jump, Caitlin called it, right? Very nice. So, anytime the function has different values from the left to the right, that doesn't
So if it was
exist.
like a piecewise.
It depends on where you're looking.
Yeah.
If that's right on the edge, it might be an issue. If it's not on the edge, that'd be okay. What about this one if I take the limit as x approaches 3?
That's
We're
fine.
going to get something. What about negative 2? I'm going to get something. Yeah. Okay. Here, Caitlin mentioned asymptotes. If I take the limit as x approaches, let's call this 4. If I say the limit as x approaches 4 on h of x, that doesn't exist. Why?
Because an asymptote is infinite.
I'm going
They're both
down there. It's
approaching
infinite.
negative.
It's not approaching a single value.
They're approaching
It doesn't
negative.
exist. Now, I said last year you could say this equals one other thing. What is it? You could say negative infinity, and AP will accept either answer. They don't care. So I'm not going to say you should do one or the other. I personally actually like the negative infinity because it gives me a little more information
I
about
told you
the
there's an
graph.
asymptote, not that.
Yeah, and it tells me that it's going that way towards the asymptote too. So I like that. But this one, if I call this, I got g, I got h, I'll call this z of x. If I take the limit of z of x as x approaches 5, you're approaching like
That's
1, 2, 3.
It's getting
Okay.
closer and closer and closer, but never.
Yeah,
quite
it is,
gets
but what's it bouncing? Is it approaching any specific value? It's oscillating more and more and more between this and this, this and this, this and this, this and this,
So
this
that
and
just
this.
gets
It's not
infinite.
approaching one specific thing again.
It's just staying.
So that doesn't exist because it's bouncing back and forth. In this case, it looks like it's bouncing between y equals 1 and y equals 3. So that
It's just
doesn't
bouncing
exist because it's
like
not approaching a
more
single
and more and
value.
more.
Just like over there, was it approaching a single value from the left and right? No. Not approaching the single value from the left and right. It's up there, then it's down there, then it's there, then it's there, that kind of thing. Okay? So those are all some issues that you can have with limits. Now we'll talk about a more precise, higher level version of limits tomorrow that won't be on the AP test, but I just want to give you an idea of how to prove things with limits, but we'll talk about that tomorrow.
Excuse me,
Yes,
on the AP test, how many questions are multiple choice?
I believe.
Is that the assignment if we want to start?
Yes, that's the assignment.
We did not want wood. That's why.
No, that doesn't do with that. That's not saying that. Oh, this has never happened to me, or this never happened.
I've never been doing an assignment out of state.
Okay, there's two problems in this assignment that matter more than any others. There's not a lot of limits on the AP exam usually. There's a couple little problems. It's not a like huge topic. But there is one type of problem in this assignment that could definitely be there. 25 and 26. Those you need to pay special attention to. We'll be looking at those kind of problems over the course of the class, and AP really likes those kind of problems. 25 and 26. Okay, so those are big ones. Okay, this isn't going to be due till Monday, so plenty of time.
Once we got half done, Kyle.
Oh my god.
You used to say that, Mr. Mark.
What would he
Mr. McGee, did you ever hear Mr. Park's motto, once begun, half done?